This is a draft science video, so please be gentle. Just playing around with some ideas. Alright, so if you don't like science stuff, then ignore this. So I've been thinking about the subject of wavelength and frequency and all that kind of stuff, and just trying to figure out in my head how to visualize it better, or combine it with the whole quantum crap and all of that stuff. So anyway, traditionally, I mean, as I was taught, or as I saw when I worked in electronics, a frequency or a wavelength is sort of visualized like this, so a sine wave. And so presumably, like when you looked at it, you used electronic device to read a signal's frequency or something, this is what you saw on a little cathode ray tube, a little green tube you would look at. You'd see a little sine wave like this, because that's how the electronics interpreted what you were looking at, and this is how it gave you information regarding the signal. But you weren't looking like a microscope, you weren't looking at reality, you were just looking at an instrument's interpretation of reality. And so what would mark this would be the ends of each wavelength, or you could argue that the ends would be at these peaks of a high and a low. So, are between two highs, as the signal went. So anyway, that's like how it was visualized, and it's just, I'm just arguing, okay, let's just throw that out, because that's just an artifact of the instrument. It's not really a proper way to look at it scientifically, because the matter isn't flying through space in some sort of sine wave. That's just the way we see it when we try to view it with an instrument. Alright, so getting to the point. So I'm thinking about this whole electromagnetic spectrum, which goes from, like radio waves up to like gamma radiation or something, or, radiation, period. What's this stuff made out of, and what's this frequency stuff, and what's this wavelength stuff, and how do you make sense of what energy these things have? And the weird part is that you can carry other information on them. So if we went back to that traditional sine wave, what radio stations were doing basically when they send you a signal was they were putting a bunch of information on that signal. So they would be able to recognize a signal based on these little the ends, and then they could put information on the signal and then pull that information back off on your receiving device, and that's sort of how you got the information. And so we're doing the same thing now, but we're using much higher bands. Oh, I did not want to hit that button. That was a big mistake. There, okay, I'm back. Lucky. Alright, sorry about that. It's interruption. Yeah, I meant to just make the drawing go away, not the whole thing. Alright, anyway. So this is how I'm visualizing. So let's say the speed of all these things are the same. A radio wave, a light wave, and a gamma ray or whatever. They're all moving at the same speed. So theoretically, there's got to be something else that's determining their frequency or wavelength. And so what I'll visualize here, let's say this is a 1 meter radio wave, and it has two marker photons that decide the wavelength, and it's the distance between them, or how long it takes in a given moment of time, in a given line of time, how long it takes the two photons to pass by, and that would be the wavelength. And so in the case of like a 1 meter radio wave, it would, in the amount of time that light travels, 1 meter of the wavelength, I'm going to say this wrong again. Well, anyway, it's 1 meter between the marking photons. Okay, just leave it at that. And then in between them, like, I'm going to speculate that in between every bit of the electromagnetic spectrum, there's the same amount of minitons in between the two that are kind of holding the two together, and that that number is always consistent. So if let's say there's 10,000 of these little minitons in between the two photons, that mark the wavelength. So let's just say this is a 1 meter radio wave. A light wave would be much tinier. I mean, so small I couldn't draw it, but we're just going to draw an example and just call it light. So light would have smaller marker photons, and it would have a much shorter distance between them. So in a given moment of time, more of these will pass than these. Obviously, it's many times more. So in the case of light, like say if this is 1 meter, a light wave is so compressed, it would be, I couldn't even put my fingers so close together to make a wavelength of light. So it's tiny difference. So this scale is way the hell off. It's like the difference between a piece of dust and a sun or something. I mean, it's a really huge difference. But anyway, the number of little whatever photony mini thingies in between them is still the same number, and so now they're just more compressed. So theoretically, let's say you can only have, so this is why, like say a AM band radio could only hold so much information, because there was still only so many dots in between these two marker photons at a low frequency. And if you made the frequency higher and got to FM band, well then you had a shorter distance, sort of like this, a shorter distance, but you could still have the same amount of information in between the two. So in a given second of time, you could read more information, because you would have twice as many or 3 times as many wavelengths of information would be passing at any given moment. So this is much slower in the amount of information it passes. Even though it's moving at the same speed, the information is stretched out. And that's, I guess, the best way to look at it, is it's stretched out. And then in light waves, it's more and more compressed, and then as you go up the scale, it's more X-rays, it's more compressed and more compressed. And so I don't know what the practical limits are, because I don't know what all the rays are, but there's some point, I would suspect, where you don't get to go any lower. So even though I can't make really small dots here, these would be the same number of dots, just closer together and closer together. So that's basically what I'm speculating is where so when you have a carrier signal, like a radio wave or a light wave or something, the information is basically held in the energy level of each one of these little thingies in between, these little mini photony things. So even these all could be photons. It's just that the marker photons are substantially larger than the in-between photons. So let's say the smallest photon is this little size, and then the biggest one could be this. Let's say the smallest one could be the size of the Earth, the biggest one could be the size of a sun. So these are just basically the same thing. They're just smaller versions that are always in between these two bigger marker photons. So I guess it would be a point where the marker photons would be the same size as the smallest in between photons, so you can get any lower, so you have no way to keep the photons together or the signal coherent. So I think that would be my speculation as to how this thing works, but who the hell knows. So I don't know if that was at all helpful. I'm just trying to think about the way time passes and how energy is moves through environments. And so this sort of also explains why some parts of the electromagnetic spectrum are able to pass through solid substances and some aren't. It's because the bigger these marker photons are, that's the real limiting factor, is they're so big that they can't get through the matter. And these real small ones obviously you could think of it in terms of just that simple, is that a little small one could find lots of ways to get through something where a bigger one couldn't. So it sort of makes it it's made frequency and bandwidth a little easier for me to understand, wavelength anyway. And I don't know where I'll go from here, but anyway, it's just one of the draft science videos. So if you have any input, please make it rational and reasonable. And if you're just going to be a cranky fuck, then buzz off. So I'm not in the mood for that shit. But anyway, that's the end. Thank you very much.